Now I want to take you into a completely new concept which is very, very important. Okay, this is called the magnitude squared response. Magnitude squared response. Okay, I'll show you in a minute what is the reason for this particular discussion, but first let us start. The magnitude squared response means HE of j omega magnitude squared, the magnitude response squared for the LTI system. This is given by HE of j omega H conjugate E of j omega. Okay. And two things to note, that if H of n has got a dtft given by HE of j omega, then what is the sequence that produces H conjugate E of j omega? Okay, if you go back and look at our properties, this is H conjugate of minus n. Okay, so this is the discrete time Fourier transform of H of n. This is the discrete time Fourier transform of H conjugate of minus n. So H of n conjugate convolved with H conjugate of minus n, this is what produces for us HE of j omega. Okay. Now this is a convolution, but remember, when you flip things around, this will become like an autocorrelation, which is a sequence that we have studied. Okay, so basically the magnitude squared response corresponds to the discrete time Fourier transform of the autocorrelation sequence. More importantly, if I ask you to write this in terms of the Z transform, okay, H of n conjugate H conjugate of minus n in terms of the Z transform, this will have a Z transform given by H of Z, okay, multiplied with the Z transform of H conjugate of minus n. Look at the properties of the Z transform. This will be H conjugate of 1 by Z conjugate. H conjugate of 1 by Z conjugate. Okay, and you can substitute Z equal to E of j omega, and you can verify that H conjugate of 1 by Z conjugate at Z equal to E of j omega is the same as H conjugate of E of j omega. Okay, you can verify that we are getting exactly the same expression. So if I am looking at the magnitude squared response, it's the same as saying I am looking at the product of H of Z, H conjugate of 1 by Z conjugate. So magnitude squared response on the unit circle is magnitude HE of j omega whole squared. Anywhere on the Z plane, it will be the product of H of Z and H conjugate of 1 by Z conjugate. Okay, now comes the very important understanding of what this what the implication is. So write it down in the following manner. HE of j omega magnitude squared is the same as H of Z, H conjugate of 1 by Z conjugate on the unit circle. Okay, but now let's look at this particular expression. Okay, suppose H of Z had a 0 which is at 1 minus C naught Z inverse, had a 0. Okay, the magnitude squared function, where will it have the zeros? It will be 1 minus C naught Z inverse, 1 minus C naught conjugate Z. Okay, basically Z inverse put by conjugate it, and then you put 1 over Z conjugate, C naught conjugate Z. Okay, where are the zeros located? Z is equal to C naught, that is from here, Z is equal to C naught conjugate. Okay, and a very important observation that comes from here. Okay, so this basically says that if I have a transfer function with a 0 at C naught, okay, oh by the way, this is 1 by C naught conjugate, okay, and not C naught. This is at 1 by C naught conjugate. Now, where is 1 by C naught conjugate? It is at the reciprocal location, same angle, because you're taken the conjugate, so reciprocal conjugate. Now, if you remember the property of all pass functions from the property of all pass functions, all pass functions, the 0 inside the unit circle and the 0 at the reciprocal conjugate location have the same magnitude response, right? That's why the ratio gives you an all pass function. So from a property of all pass functions, okay, and that is a important aspect for us. So for example, if you had a all pass function which is of the form 1 minus A star Z divided by 1 minus A Z inverse, okay, these two have got the same magnitude response. These two have got the same magnitude response. The 0 inside the unit circle and at the reciprocal conjugate location. This is from a property of all pass. Now, of course, magnitude squared response also means that the He of j omega and H of j omega conjugate must have the same magnitude response. Both of these have the same magnitude response. So if H of Z, so here are the important rules about the, so observations about magnitude squared transfer function. Observations about the magnitude squared transfer function. Magnitude squared function. Okay, here it is. Let us first make an observation about zeros and poles. Zeros and poles. Okay. If C naught is a 0 or a pole, the magnitude squared transfer function will also have a 0 or a pole at 1 over C naught conjugate. Is also a pole or 0 or pole. Okay, 0 or a pole. Magnitude squared transfer function, we just now showed that wherever you have a C naught, there will be a reciprocal conjugate 0 also, or a pole. So basically this is an important statement. Okay, second, if H of n is real valued, okay, then what you will find is that then C naught cannot be just conjugate, it will occur as a complex conjugate pair. Only then the pair will give you zero value, real valued complex coefficients. Then the magnitude squared transfer function will have 1 over C naught conjugate and 1 over C naught. Okay, so basically the reciprocal conjugate location will also be there. So what this says is the magnitude squared transfer function will have C naught 1 over C naught conjugate, the reciprocal conjugate pair. It will have C naught conjugate and it will have the reciprocal conjugate, which is 1 over C naught. So basically it will occur as a set of 4 where you have the complex conjugates. So you will have the complex conjugate pair inside the unit circle and also the reciprocal, which is outside, if it is real valued. Okay. Now third one, if the 0 happens to be on the real axis, if the 0 is on real axis, 0 or a pole. Okay. So then what you have is a 0 here, the reciprocal will also be present, 0 or a pole. Okay, 0 or a pole. The reciprocal will also be present in the this thing. Okay, number 4. If it is on the unit circle but not on the real axis, on the unit circle but not on the real axis. Okay, then what happens? It will be here, the reciprocal conjugate will fall exactly on the same, so it will be a double 0. And if it is real valued, the conjugate will also be present. That will also be on the unit circle. Its reciprocal conjugate will also be there. Okay, so it will C0 conjugate will occur as double zeros. Okay, we're not talking about it as poles, because if it's a pole on the unit circle, it will become unstable system. So really, when you talk about on the unit circle, it's typically the zeros that we are talking about. Okay. Last, I don't have space here, so let me move on to the next page. Okay, this is observation number 5. If you have a 0 at plus or minus 1, 0 or a pole, okay, then it will be again a double 0 or a pole. What do we mean by that? If you have a 0 sitting here, reciprocal conjugate will also be there. Or if you have a 0 sitting on the unit circle on this side, again you will have a double 0. So magnitude squared transfer function has got a very unique set of properties. Let's just summarize it in terms of the zeros. You can always extend it in terms of the poles. The 0 and reciprocal conjugate will be present. If it is real valued, then C naught conjugate will be present, right? And the reciprocal conjugate will be at 1 over C naught conjugate and 1 over C naught. So basically they occur as a 4. Now if it is on the real axis, you will find that the reciprocal is C naught and 1 by C naught. Okay, those are the reciprocal conjugate pairs. Otherwise, what you will find is that they are at C naught, 1 over C naught conjugate. They are lying at the same place. C naught conjugate and 1 over C naught, they are also lying at the same point. And the final one is both are at this place. So this is C naught 1 over C naught. Okay, basically the reciprocal both are lying on the same point. So magnitude squared transfer function has got a very unique, very distinct set of properties, and we want to be able to understand and capture what the implications are. Now, why did we spend so much time on this particular aspect? Let me explain it in the form of an example. Okay, we have an example here where I'm going to give you the pole 0 plot. Okay, here is the pole 0 plot. It's a magnitude squared transfer function. H of z, H conjugate of 1 by z conjugate. Okay, and the first set of zeros are on the real axis reciprocal conjugate pair. The second one are at, it's a complex conjugate, so you will basically see these values. These are poles. Set of pole here, the reciprocal conjugate, the conjugate and its reciprocal conjugate. Okay, and there is a real valued pole on the negative real axis, its reciprocal is there. Okay, and two more poles, two more zeros. Zeros are located okay. So, how many poles, how many zeros? There are the transfer function h of z has got 3 poles and 3 zeros. Okay. When you look at it as a magnitude square transfer function h of z, h conjugate of 1 by z, this will have 6 poles, 6 zeros. Okay. Now, the whole idea is that we are trying to find out what are the ways in which we can obtain the transfer function h of z. Okay. So, how many possible number of possible ways in which possible values for the transfer function h of z. What do we mean by that? We are given a magnitude squared transfer function. You can take either the pole inside the unit circle or the reciprocal conjugate. You can take a 0 inside the unit circle or its reciprocal conjugate. Regardless of whether you take the one inside or outside, you are going to get the same magnitude response. So, how many transfer functions are possible? So, for each of the 3 poles, I can take inside or outside. Each of the 3 zeros, I can take inside or outside. So, at the end of the day, I can get 2 to the power of 6 transfer functions, which are possible in terms of which all of them will have the same magnitude response. Okay. Only you can for each of them you take the pole inside or the one outside at the reciprocal conjugate location. So, a total of 64 transfer functions are possible if we just say that given this magnitude squared response, how many h of z's can you obtain which will satisfy this condition for the magnitude squared response? It will be a total of 64 transfer functions. I hope you are able to visualize that. I want you to think about this and apply it. Okay, so first one, if I impose the condition number of possible transfer functions with real coefficients. With real coefficients. Okay. So, now there is a condition that I can either take the complex conjugate pair inside the unit circle or the complex conjugate pair outside the unit circle. I have to take it as a pair. Okay. The ones on the unit circle are independent, so therefore I can treat them. So, now how many independent choices do I have? I have one 0 on the unit circle, I can take inside or outside. The other 0 I have to take it as a complex conjugate pair, so that together they become one option. Similarly for the pole. So, there are a total of 4 possible options. The 0 inside and outside, the complex conjugate zeros inside or outside, the pole inside or outside, the complex conjugate pair inside or outside. So, this is 2 to the power of 4, which is 16 transfer functions which can satisfy the condition that I have a complex conjugate, I have a real transfer function. That means the complex conjugate zeros should occur together. Okay, now supposing I impose the condition that I want the transfer function to be stable. Transfer functions which are stable, which are causal and stable. Causal and stable means all zeros inside the unit circle. Okay, so there are no choices with respect to all the poles are inside the unit circle, sorry, all poles. So there are no choices with respect to the poles, they are fixed. So h of z will have all the poles inside the unit circle. What are the choices that you have? You have the choices that the zeros can be inside or outside. We did not specify that they have to be real coefficients. So basically all poles inside the unit circle, zeros can be anywhere. Okay, so this basically tells us that there are 2 to the power of 3, which are 8 transfer functions. The 3 zeros, you can take the one inside or outside, all of them will give you the same transfer function. Okay, finally, the number of possible transfer functions that are causal, stable and real valued and real coefficients. How many such combinations can you find? Real coefficient. Okay, now that means the zeros and the poles have to be taken as complex conjugate pair. The poles anyway are constrained because you can only take inside the unit circle. So the 0 that's on the real axis, inside or outside. The complex conjugate zeros you can take inside or outside. There are basically only 4 choices. So 2 to the power of 2, that's equal to 4. Now, what are we saying? I gave you a magnitude squared transfer function with a total of 6 poles and 6 zeros. If at every choice you take either the 0 inside or the one that is outside at the reciprocal conjugate location, you will get a total of 64 transfer functions which will satisfy this magnitude squared transfer function. Okay, something that you may not have thought about. So there are many transfer functions which are satisfying the same magnitude squared transfer function. Now in this, if we impose the condition that it should be causal, stable and real coefficients, then you get only a total of 4 possible transfer functions which will satisfy the same magnitude squared response, but at the same time will be causal, stable and will have real coefficients. Okay, I hope you are comfortable with that. This is something that I would like you to think about very, very carefully and make sure that you are understanding this in a very thorough manner.